again, everyone, this is Professor Bell with you, and I'm going to walk you through your first lab assignment. And so just so you know where to find it, this is the home page. Click on Content, and then just scroll down. Well, the lab documents was the last page I was on, so it's popped up here. But you'll note here down at the bottom of the modules, quizzes, and then labs are here. So this is your form. So if you'll just click this, it should open up and look like this. I've put it into Paint so I could actually show you a couple things with the whole thing. And this is about the only way I know how to interact with it. We would have normally been doing this together in class. I would have put you in pairs or working groups to share this information. But I'm just going to have to do it this way for now. Sorry about it. That's the pandemic. Okay, so here's what you need to know. Well, make sure you watch those two videos that I have in Module 1 showing you about latitude and calendric time and longitude and 24-hour clock time. And that should help you with the time-space stuff. Anyway, when you're looking at a address like 36 degrees north and 86 degrees west, this is always going to be latitude is first, so north and south, of the equator, which is the baseline. Here's 0 on that line on the globe, and so that's where we start counting from, and we work our way from that line all the way up to 90 degrees north. So pay attention to the lines and the numbers here on the sides and top. Okay, so that is the North Pole. There's nothing above that, and in fact, this is all stretched out in the form of this map, becoming about 25,000 miles, when in fact it's a pinpoint on just the surface of the Earth. But that's how we have to flatten out Earth to represent it in such a way. Anyway, that is latitude. Longitude's always the second number, and so that's counting from the baseline, which is actually in Greenwich, England, which is kind of a subset of London, but that's forming here for you the baseline for the Eastern Hemisphere if you're traveling into this area of the world, or the Western Hemisphere, which is over here. Okay, so putting that into play, let's take a look. And so we're going to start from the equator on 36 degrees north latitude. So here is 30, there is 40. So you're about halfway between the two, but a little tick higher up to 40. So your line would be somewhere right around in here. So you might just draw a little dot or something, but think about a line being formed here. Let me see if I can get this for you. So the line that would be, of course, parallel to where you'd find that one. I wish I had put that as red. Let me see if I can change it to red. There we go. Okay, then if we look for 86 degrees west, here is 0. That's your prime meridian. And so, and by the way, this is from 0 going north is northern hemisphere, and 0 south is the southern hemisphere. Also take note too, this map cut off. They cut all of Antarctica off, so it only goes to 60 degrees south. If you were to see Antarctica in this representation, it would look like a huge, gigantic continent down here on the bottom, when in reality it isn't. Anyway, that said, 86 degrees west, so this is the direction of west. So from 0, 10, 20, 30, 40, 50, 60, all the way over here to 90. So 86 is going to be somewhere right around here in the middle, and where it intersects is, of course, where you're going to put your dot. And if you don't know, that's basically where Gallatin is. Okay? So in looking at that, then let's see if I can put a dot here. Basically where that intersection is where you'd want your dot to be. Okay, so I'm trying to fill everything in here just so you have something as a record to look at. Okay, so that's it. Plot and label it, so put your label on it, and then do that for all the rest of these. Now let me explain this number 7 to you real fast. This, because I said time is space and space is time, this is literally what we're seeing here. So if you know how to tell time, you know how to tell distance. So this is like the hours, minutes, and seconds on a clock. Okay, but instead of hours, we have degrees, and these will never go for latitude above 90 degrees north or south. That's as high as that number will ever get. And there wouldn't be, if it's a 90, there wouldn't be any minutes and seconds. But as we break apart the minutes and seconds, as you move forward, so whatever, if you're in between lines, you would see that 52 and 1 minute would be just a tick above 52, and 59 ticks away from the next full line of latitude, which would be 53 degrees. So this one is about a quarter of an hour, if you will, 17, not 15, but this would only go up to 60 is what I'm trying to say. So once you get to 59, and then over here, this is seconds. So in the same way on your clock, if it goes from 30 seconds and this is 17, then you go up to 59 seconds. What comes next on your clock is 2 zeros, and then you move to 18. And it's the same way over here with longitude. The only difference between latitude and longitude is that this number in longitude can go to 180. Why? Because here's the prime meridian. Okay, it's measuring distances east and west of the prime meridian, and it goes all the way to 180. So that line right there and that line right there are the same, and they're stitched together. So this is the eastern part of Russia right here, and here is where it would connect. Okay. So this said, this is a very small scale map. It's showing showing the entire Earth, but not a lot of detail. So you really would have a difficult time finding something so specific as 17 minutes and 30 seconds. You'd need a map that would be closer to the size of, say, just the southeastern United States or whatever, to be able to accurately locate these little minutes and seconds here. I'm just trying to expound upon how this works, though. Okay, so again, just imagine for, say, this one at 23 degrees north latitude, that 50 minutes of that means you're 5/6 of the way between 23 and the next line, 24, going north. Okay, so that said, when we look here, I said going north. Shoot, sorry, east. Sorry. But again, trying to understand what that looks like on the map. I didn't consider this. I might already even show you that. Maybe I should do that. I'll see if I can put something on at the end and do that for you. But anyway, find these locales, connect on number 8, all 3 of these in the triangle. And what I will tell you is it represents something called a bread basket. And when you get it, you'll know where that bread basket is of agriculture. So I'll leave it at that. And this is pretty self-explanatory, I think, by now. Looking over here, there's several things we'd need to do on this page, and that is we're looking at the globe and velocities of it, okay? So label your lines of latitude, okay? So when you see the lines of latitude, well, what are they? How do we know what's what? All right. So over here on the first map, it was all labeled out for us, right? But you don't have all of those lines as you did here at 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees going north. So what we need to do then is figure out what is the distance or the difference between 90 degrees and wherever this baseline is. So where does the 0 line, the equator, where does it go? Well, it bisects the entire globe. So that right there is your equator. So if I were to put here, this is what I mean by labeling your map. You're going to put 0, 0, and I don't have the option for a degree, so I'm just going to write degrees, okay? So 0 degrees, that's that line, okay? So let me see if I can fill this thing with white so you can see a little bit better. Maybe I didn't do that. Oh, opaque, that's it, sorry. Okay, there we go. So that's not what I wanted to do. There we go. So let me just enter it that way. But you would just put 0 and then the little circle degree up here. So that's 90 right up here. Then you need to be able to figure out what is the where exactly what are the numbers of this line, this line, this line, this line, this line. Okay, so I'm leaving that to you to figure out. Also, I've asked you to write in the rotational velocities as well. So we're figuring out those right in here. But on the globe, draw your arrows in the direction of the Earth's rotation. So I'll do that one for you as well, if I can here. So if I just pick this line right here, I would just put, an arrow doing this. and this, because we know the Earth turns in this fashion, that it's later on this side of the globe than it is over here. So the inauguration, for instance, is going on in Washington, D.C. It's an hour later there than it is here for us in Gallatin, or for anyone living in Colorado, or another hour even after that. So this is, as I'm doing this, it's about 2 o'clock here Central Standard Time, so it's about 3 o'clock here, 2 o'clock here, 1 o'clock here, 3, 2, 1, and noon. It's just almost noon right out here in California on the West Coast. Okay. Answer your questions about directions, and then looking at these answers right here, knowing that 25,000 miles is the girth of the Earth, which is to say where the equator is right here. So we know that distance matters, and so dividing this stuff together, well, would make sense in seeing what the speed is. So let me write this out and then I'll come back. Okay, so here we are, gang. I've gone back in here and essentially solved this problem for you. So looking at 24,900 miles around the equator, a full rotation on the axis takes 24 hours. So I divided the first by the second, and this gives us a rotational velocity here of Earth at the equator being over 1,000 miles an hour. Now, I think that's pretty straightforward math, but you'll find that it's not so straightforward once you start looking at changing the distance between those lines of longitude, the length, that is, of 1 degree of longitude at certain areas north or south of the equator. Okay, guys, we're back here at it again. So I wanted to pause for a second to get something straight in my mind. So what I want you to do now is to try and calculate these velocities, knowing, obviously, if you're standing at one spot on the top of the planet or on the bottom, 9 degrees south, and it still takes 24 hours to do a full revolution, then this is just you standing in one spot, spinning very slowly 360 degrees at the north and south poles. So I want you to think about it for a second. If you were to look from the top down, North Pole down on the globe, and see the outside is the equator, you can only see half the Earth at once. So the outside it's kind of like a bullseye. So the equator would be the outside of that ring, and the bullseye would be the North Pole. So the outer part that you'd see has to go faster to do 360 than those other smaller circles on the inside. It's kind of like why they stagger the start in a race around a track, with the outside runner getting what seems to be a much greater lead on the person that's on the inside lane, but they're still running the same distance. It's just the one on the outside's got to run faster. So this is to say, pause this video and see if you can figure out these velocities on your own. I would have given you hints or something like that while we're in class. We can't do that, but I want you to pause it and think about it, and then I'm going to come back and show you how to calculate these. So pause it now, and I'll see you in a second. Okay, so we're back again, and what I've done here is I've worked on 15 degrees north latitude. So I did what I'd done before, which was to take that number and divide it by 24 hours. So here's your 67 miles, that degree, the length between a degree of longitude, and what you can see here is your answer comes up wholly unsatisfactory. If the equator is moving at over 1,000 miles an hour, it should stand to reason that 15 degrees north of that still should be going pretty darn fast and not less than 3 miles per hour. So there's one other component that has to be added in, and I'm wondering if you figured it out, but I'm about to show it to you again. If you want to try to figure it for yourself, you're welcome to, but here goes. So I had to copy and paste this to make sure it wasn't there. So you have to add in the circumference again of a circle and multiply that by 360. So at 15 degrees north latitude, the speed of rotational velocity is still over 1,000 miles an hour. It's 1,005. Okay, and so you should be able to figure the rest of these out on your own now, and give it your best shot. This is your work to do now. I don't provide all the answers. You do get a grade for it, But you can ask questions about it too if you want. Maybe I'll put up a discussion board about labs or something like that. But again, I don't think it's for me to give you all the answers. So I've given you just enough to be dangerous. All right, guys. Have a good one. See you later. Bye.